In the previous video, we introduced the Algorithmic Lovasz Local Lemma. In this video, we'll sketch the proof. Actually, we're going to sketch the proof for a special case, the special case for KSAT. More precisely, we're going to prove the following. Suppose that phi is a KCNF formula on n variables with m clauses. For example, maybe phi looks like this. Where there are k literals that show up in every clause. And where our underlying variable set is x1 up through xn, and there are m total clauses. Further, suppose that each clause, c, in phi, shares variables with at most d+1 clauses, so d clauses and c itself, where d+1 is equal to 2 to the k minus c for some constant little c. Then, what we're going to show is that first, phi is satisfiable, that is, there is a way to choose values for x1 up to xn so that phi evaluates to true, and moreover, there is a randomized algorithm that will find a satisfying assignment running an expected time polynomial in n and m. One can be much more precise about the running time than this, but the point of this video is just to sketch the basic idea of the proof, so we're not going to worry too much about it. Here's a version of the algorithm that we're going to use to prove the theorem. This is just the algorithm from the previous video, specialized to KSAT. So here's the algorithm, given a formula phi. We're going to choose a random assignment, sigma, for each of the variables that appear in v, x1 up through xn. And while there's some clause c in phi that is not satisfied, we're going to update our assignment sigma by just randomly reselecting the variables that appear in c. We're going to do that until, hopefully, this while loop terminates. We'll cross our fingers and just hope that it does. And then we'll return sigma. So obviously, if this algorithm does terminate, it will have found a satisfying assignment. Thus, our job is to show that it terminates, and in particular, that it terminates reasonably quickly. Here's the proof idea. So the proof that we're going to sketch today in this video is due to Moser. It's often called Moser's entropic proof. It's different than the proof that actually first appeared in the original paper. So you can find a pointer to the original paper in the lecture notes, and I encourage you to check that out if you're curious to see how that one goes. Okay, but here's the idea for Moser's entropic proof. We're going to take the algorithm that we had on the previous slide, we'll modify it a little bit, and in particular, we're going to add some print statements to it. Thus, we can view the algorithm like this. It's a box labeled algorithm. It takes as input a formula phi, and spits out as output an assignment sigma. Additionally, as sort of an auxiliary input, if you like, it's going to take in some random bits, which it's going to use to re-randomize the assignment as it goes along, and it's going to, along the way, output some print statements. So the natural way to view this algorithm is kind of in this direction. This is the input, this is the output. The idea of the proof is going to be to view it in this direction, so thinking of the random bits as the input and the print statements as the output. What we're going to show is that looking at the algorithm this way, if it runs for too long, it's actually going to be able to compress these random bits that it took as input. That is, suppose that it takes n random bits as input. What we'll show is that if the algorithm runs for too long, it's going to output significantly less than n bits worth of information in these print statements. Moreover, we're going to show that given these print statements, one will be able to recover the original random bits that went into the algorithm. This is going to lead to a contradiction, because it's going to imply that I can take a whole bunch of random bits and compress them into not so much information in a way that allows me to completely recover all of the random bits. It turns out that we can't do that. So that will be a contradiction under the assumption that the algorithm runs for too long. Therefore, the algorithm can't run for too long. This is an extremely slick proof strategy. In order to instantiate this proof strategy, we're going to modify the algorithm a little bit. In particular, we're going to write it as a recursive algorithm. So let's call it algorithm prime. Our main procedure, called findSat, is going to work as follows. So it takes as input a formula phi, which is the and of a bunch of clauses. It's going to choose a random assignment sigma for each of the variables x1 up through xn that appear in phi. And then for each clause ci in phi that is not satisfied, it's going to run some procedure called fix, which I'll define below in a moment. Once it's done with that, it will return the assignment sigma that results. Okay, so what does the procedure fix do? Well, it's down here. So this is a recursive procedure. So fix is called on a formula phi, a clause index I, and an assignment sigma. The first thing it's going to do is to update sigma by re-randomizing every variable that appears in the clause ci. Then, it's going to look at all of the other clauses, at most d+1 of them, that share any variables with ci. Here, we're using the assumption that at most d+1 clauses, including ci itself, share any variables with ci. Now, for j equals 1 up to d+1, if the clause cij is violated, I'm going to recursively call fix on that clause. Sorry, this is a typo. This should be I sub j. That's very important. And I'll use that recursive call to update sigma. Finally, when I'm done fixing all of these clauses, I'm going to return the final assignment sigma that I get. So this algorithm is essentially doing the same thing that the earlier algorithm did. It's just for some reason I'm writing it in this weird recursive way. We'll see why in a moment. One way to think about what this fix function is doing is that I'm going to try to fix the clause ci, and in doing so, I might accidentally break some of these other clauses. These are the clauses that I could possibly break by re-randomizing the variables that appear in ci. Then I want to clean up any mess that I've made, so I'm going to recursively call fix on all of those clauses that I might have broken. That's sort of what's going on here. So hopefully you can see that if this algorithm terminates, it's going to find a satisfying assignment, because I will go through all of the clauses that are broken, and I'm just going to fix them. And I will recursively clean up any mess that I make when I'm trying to fix them. So the goal is going to be to show that the algorithm does indeed terminate, and then does so quickly. Just to make sure we know what's going on, let's step through an example of this. So suppose we have this formula phi, which has 4 clauses, C1, C2, C3, and C4. The first thing we're going to do is choose a completely random assignment. Let's say x1 equals 1, x2 equals 0, x3 equals 0, x4 equals 0, x5 equals 1, x6 equals 1, x7 equals 0, x8 equals 1. And I'm going to write the values of the literals on top here. 1, 0, 1, not x1 is 0, x4 is 0, not x5 is 0, and so on. So the first thing we do is we look for unsatisfied clauses. This one is unsatisfied. This is the first one that's unsatisfied. So at the top level, we're going to call fix on this clause. Now I'm going to re-randomize the variables that occur in this clause. That's x1, x4, and x5. So let's say I re-randomize those to 0, 0, and 0, respectively. I'm going to highlight these so that we remember that these are the new random bits that I flipped. That's going to come up again later. And then I'm just going to fill in the rest of the new assignment that we get just by copying things over. And then I've just updated the values of the literals up here appropriately. I realized that before I accidentally had a 1 here for x3, it should be 0. Okay, so this is great. We've fixed clause C2. It's now satisfied. But unfortunately, we may have broken some other clauses. So that's where we need to use our recursive calls to fix to recursively fix those. Now, there are two clauses that share variables with C2. There's C1 and C3. So fix is going to potentially look at two different clauses, C1 and C3, that it might have to recursively call fix on. When it goes to C1, it finds out that indeed C1 is broken, or C1 is violated. So it's going to call fix again. That means that we're going to re-randomize the variables that occur in C1, x1, x2, and x3. Let's say that those become 1, 0, 1, respectively. And again, I'm going to highlight these to indicate that these were the new random variables that we drew. And all the others I'm just going to copy over. And I updated the values of the literals here. Cool. So now we've fixed clause 1. It's no longer violated, but once again, we might have to recursively clean up any mess we made. Clause 1 shares variables with two other clauses, C2 and C3. So I might have to go and take a look at each of those. I go and look at C2. Fortunately, it's not violated. So I don't need to recursively call anything. And then I go and look at C3, and oh no, it is violated. So I'm going to call fix. Now I'm going to re-randomize these variables, x2, x3, and x5. Let's say that I re-randomize them to 1, 1, and 0, respectively. Once again, I'll highlight them to indicate that these were my random coins, and fill in the rest. 1, 0, 1, 0, 1. And I updated my literals up here. Okay, once again, maybe we need to go recursively clean up any mess we've made. C3 shares variables with two other clauses, C1 and C2. Now, fortunately, both of these clauses are actually satisfied, so we don't need to recurse anymore. Now we'll be finished with this recursive call to fix, so we'll pop back up to this one. Now we're done with this recursive call to fix, so we'll pop back up to this one. Now this recursive call to fix still needs to go take a look at C3. Fortunately, at this point, C3 is not violated. So now we're done with this recursive call as well, and now we're done with the whole thing. And hooray, at this point, we've found a satisfying assignment. It's this one here. Okay, so that's the algorithm. Probably you didn't need me to step through it to understand what it's doing, but these details are going to come up a few more times, so it's good to see them now. The reason those details are going to come up again is because we're going to modify the algorithm. Actually, we're going to modify it in a couple of ways, but the first thing I'm going to do is add some print statements. So I'm going to add the following 3 types of print statements. First, before I make a top-level call to fix, I'm just going to print out fixing clause I. Then, in the recursive calls, if I get to some Cij that's violated that I need to recursively fix, I'm going to print trying to fix the jth child. So it's important here that I'm printing trying to fix the jth child and not trying to fix the ijth child. We'll see why later, but basically it's because j can only take on d plus 1 possible values, so I only need log d plus 1 bits to write j. If I wanted to write ij, I need log m bits, which would be a lot more. So this is really the key to why these print statements are going to compress things, is because I'm getting away with actually printing a lot less information here in terms of bits than I would be if I were to just report the clause that I were fixing. Finally, when I'm done with all of my recursive calls, cleaning up all the mess I made, I'm going to print all done, moving up a level of recursion. So let's return to this example and see what this looks like. Just seeing what the print statements would be. The first print statement comes with this first call to fix. I'm just going to print fixing clause 2. Then I went down here, and I had to fix the first of 2 possible neighbors. So I'm going to print fixing the first child. Then I go down here, nothing interesting happens. I go down here, and I have to fix this clause. There are, again, 2 possible things I needed to fix, and I'm fixing the second one. So I'm going to print fixing second child. Now I'm going to recursively call fix. Fortunately, I don't need to do any more work. So I'll finish that loop, and then I'll just say all done. Then I'm done with this call to fix. I return here. Now I'm done with this one as well, so I'm going to say all done. Now I'm going to return to this call to fix. I go down here, I find that C3 is not violated, and once again I say all done. Great, and then I'm all done and I output my satisfying assignment. Okay, so that was algorithm prime with some print statements. Now let's take a look at algorithm prime prime. Just one more change. I'm going to add a limit on the number of times that we can call fix. So more precisely, I'm going to define some global variable, capital T, to be determined, and I'm going to keep some counter t equals 0. And every time I call fix, I'm just going to increment this counter, little t, and if little t ever exceeds big T, I'm going to print too many iterations, and then I'm also going to print the current assignment, and then I'm going to halt. So that's the only change. Basically, this is saying I'm only allowed to call fix so many times. If I go on for too long, then just stop and print the current assignment that I have, even though it's not a satisfying assignment. So once again, let's return to this example, but now let's see how it would look if t were equal to 2. So I'm only allowed to make 2 calls to fix. Okay, so the algorithm begins just as before. I print out fixing clause 2, I call fix on it. I go down here, I say fixing first child, I call fix. I see that C2 is not violated, hooray. I come back, I go down to C3. I say, oh no, C3 is violated, so I print fixing second child. And then I try to call fix, but oh no, at this point, my iteration limit is exceeded. I'm only allowed to call fix twice, and this would be my 3rd call. So as soon as I get into this call, instead of actually going and recursively fixing things, instead I'm just going to stop. So this check doesn't happen, this check doesn't happen, I don't say all done. I don't say all done up here. This check never occurred. I didn't say all done here. We never returned this satisfying assignment. I never even chose these re-randomized bits. Those go away. History is just undoing itself. And instead, what I'm going to print is too many iterations. And then I'll print the current value of sigma. In this case, I can just read it off of the side here. Sigma is 1, 0, 1, 0, 0, 1, 0, 1. Great. Okay, so why did we do this? We took a perfectly nice, simple to state algorithm, just a simple while loop, and then we made it recursive, and then we added a bunch of print statements, and then we added an iteration limit, and then I went through it in excruciating detail like 3 times, and you're probably extremely bored. What is the point of this? The point is that now we can make the following observation. The observation is that given all of these print statements, the ones that we just saw how we'd be printing out, I claim that we can recover both the original random assignment sigma and also all of the random bits that were ever chosen by the algorithm, all the random coins the algorithm flipped. So I'm going to prove this observation by example, that same example that we just went through in excruciating detail. But after seeing the example, you should pause the video and try to convince yourself that it's true, not just in this example, but in general. Okay, but let's prove it just for this example. So here I've erased everything that we had about the execution path. All I've kept is the print statements. So here are the 4 print statements that we made in the case when t equals 2. First we said fixing clause 2, then we said fixing first child, then we said fixing second child, then we said too many iterations. The first thing we can observe is that from this information, we can figure out sort of the structure of the recursion. In fact, if you go back and look at these print statements, these might be the sort of print statements you would write if you were trying to debug a recursive algorithm using print statements. That is, given these print statements, you can figure out sort of exactly when I recursed and on what. So returning here, we see that the first thing we did was look at clause 2. So I know I must have called fix on clause 2. And then I know, because I know what phi is, that clause 2 had 2 clauses that it shared variables with, clause 1 and clause 3. The next statement was fixing first child, so I know that I must have recursively called fix on clause 1. Once again, I know that clause 1 shares variables with 2 other clauses, clause 2 and clause 3. The next statement was fixing second child, so I know that, okay, clause 2 must have been okay. I must have gone down here to look at the second child, clause 3. I know that I wanted to call fix on it, but the next statement is too many iterations, so I had to stop. At this point, I know that the assignment was 101000101. I'm just writing it down over here. Okay, so now that we're at this point, let's try to work backwards. I never got around to fixing clause 3. You can check that it's still broken with this assignment. But the thing I did before that was fixing clause 1. That means that before I fixed clause 1, right before I ended up with this assignment, clause 1 must have been violated. But there's only one way to violate clause 1. I must have had x1 equals 0, x2 equals 0, and x3 equals 0. So let's write that here. I must have had 0, 0, 0. And I also know that these must have been the random bits that I flipped in this call to fix. So going back in time, before I made this call to fix, the assignment must have been 0, 0, 0, 0, 0, 1, 0, 1. Here I'm just copying over the other things because I know they didn't change. Okay, so now let's go back in time again. The previous call to fix was this one. And I know that I called it because C2 was broken. There's only one way for C2 to be broken. That's if x1 is equal to 1, x4 is equal to 0, and x5 is equal to 1. So that must have been what had happened before. x1 was 1, x4 was 0, and x5 was 1. And I know that these were the random bits that I flipped in this call to fix. So now I can fill in the assignment that I must have had before this call to fix. It was those 3 bits and then just copying everything else over because they didn't change. So now I've basically unwound the algorithm all the way to the beginning. I know that my original assignment sigma must have been this one, 10001101, and I know that my random bits were these highlighted ones. That is, the first time I called fix here, I flipped 0, 0, 0, and the second time that I called fix here, I flipped 1, 0, 1. And indeed, if we go back to this previous slide, here's where I had worked out all of the actual execution path, we see that that is indeed exactly what happened. The only difference is that here, the progression is written this way, and on this slide down here, it's written in the other way. Hopefully, this example convinces you that you can always recover sigma, the original assignment, and always recover the bits that were flipped just from these print statements. This was a reasonably simple example because I wanted it to fit on a slide and we don't have all day. But the point of all those print statements, including the all done and so on, is that from those sorts of print statements, you can exactly recover the tree that would happen, and then from the fact that if a clause is violated, it can only be violated in exactly one way, will help you always work backwards and figure out what the original assignment was and what random bits were flipped. Okay, so that establishes sort of the observation. We're going to use that observation to prove the following claim. Consider the first time that fix is called from find_sat. I claim that the running time of that call to fix is polynomial in n and m with high probability. There also isn't anything special about the first time here. This also holds for the second time, the third time, and so on. If this claim were true, it would mean that the running time of my call to find sat is also going to be with high probability polynomial in n and m. The reason is that I'll be able to union bound over all at most m calls to fix at this top level, so just these calls. And I know that if this algorithm finishes, find_sat is going to return a satisfying assignment. That's because up here in this top level, I'm fixing all of the clauses that were initially broken, and because of the recursive calls, I'm going to clean up any mess that I make. And I won't break any more clauses. So altogether, if we can prove this claim, that each one of these sort of top-level calls to fix returns in polynomial time, that will prove that this entire algorithm works, that the whole thing runs in polynomial time and finds a satisfying assignment. So let's sketch the proof of this claim. As we mentioned before, the idea is to view this algorithm not this way, as something that takes a formula and outputs an assignment, but rather this way, as something that takes a bunch of random bits and outputs some print statements. More precisely, suppose, towards a contradiction, that it's not too unlikely that the algorithm runs for t steps. We still need to determine t. And does not find an assignment. That is, there's some decent chance that this algorithm goes on for a while before it succeeds. Let's think about how many random bits go in and how much information in print statements comes out. So the number of random bits that go in, well, that's n for sigma, the original random assignment, plus k times t, because there are capital T re-randomizations, and each time I choose little k new bits. Okay, so that's the number of random bits in. How about print statements out? So I've put the algorithm over here so that we can kind of keep track of all the print statements. So the first thing is, once we're going to say fixing clause I, that takes log m bits. That's because there are m possible values for I, so it takes log m bits to write it down. Next, how many times do we say trying to fix the jth child? Well, we say that at most t times, because every time we say it we call fix, and we only call fix t times. And the number of bits we need to say trying to fix the jth child is some constant c. That's the trying to fix the child. And then for j itself, we need log d plus 1 bits, because j can take on d plus 1 possible values. Next, we might also say all done at most t times, because we do it at most once for each call to fix, and that's just some constant. Plus t times some constant c. Here I'm using little c as like some catch-all constant, so we can make it big enough so that it covers the amount of information we need to say this, and trying to fix, and so on. So this is for all done. And finally, we need to take into account that we will once say too many iterations, my current assignment is sigma. So we only ever say this once, right before we halt. Saying too many iterations takes a constant number of bits, and saying sigma takes n bits. So that's plus n plus some other constant c. Thus, if the number of random bits in is significantly more than the number of bits we get in the print statements out, then because of the fact that we can recover the random bits from the print statements, like we just said, if it's not too unlikely that this occurs, then it's not too unlikely that I will be able to compress a large amount of random information into a little amount of print statements. It turns out that this is impossible. You can check out the lecture notes for a proof that this is impossible, or you can try to convince yourself of it now using a counting argument. But altogether, this means that we're going to get a contradiction if this value is significantly bigger than this value. That is, n plus kt is bigger enough than, this is not a very precise statement here. Check out the lecture notes again if you want a more precise statement. Log m plus t times c plus log d plus 1 plus t times c plus n plus c. Rearranging this and canceling these n's from each side, we see that we get a contradiction as long as t is sufficiently larger than log m plus some constant c prime, some other constant, divided by k minus log d plus 1 minus some other constant. Let's call it also c prime. Now we're going to use the fact that we chose d plus 1 to be 2 to the k minus some sufficiently large constant. So I'll write that up here. Recall that d plus 1 is equal to 2 to the k minus, let's say, c prime prime, for some c prime prime that we get to choose. And so that means that this whole thing is equal to log m plus c prime divided by k minus c prime, that's just c prime prime, minus c prime. Ugh, lots of primes. The point here is that as long as we choose c prime prime, which was I think just c in the original statement of the theorem, to be larger than whatever constant this turns out to be, we get a contradiction as long as t is larger than or equal to log m or so. And what was the thing we were contradicting? We were contradicting that the algorithm runs for that long without finding a satisfying assignment. So, saying this a bit more directly, as long as t is larger than log m or so, it is very likely that the algorithm will find a satisfying assignment within t steps. Altogether, that means that each one of these top-level calls to fix just takes log m-ish re-randomizations. In particular, it certainly runs in polynomial time in n and m. And so then this whole thing also just runs in polynomial time in n and m, because I just make m different calls to fix. Okay, so this is just a proof sketch. It's not a complete proof. You can check out the lecture notes if you're curious. But the main point of this was just to give you the basic idea of the algorithm. And in particular, this really cool idea that instead of looking at the algorithm as something that takes in phi and spits out sigma, we're instead looking at the algorithm as something that takes in random bits and spits out print statements. And then we just showed that if the algorithm runs for too long, it happens to be a really good compression algorithm, and you can't have compression algorithms that are too good. I think that this is such a cool proof, like such a slick statement, so I hope that you think so too. Okay, so that at least sketches the proof of this theorem, which was the special case of the algorithmic LLL for KSAT. Okay, so that will just about wrap it up for today. This video was probably on the long end, so thanks for sticking with it, and thanks for watching.